Hi everyone. So I'm going to be talking about how you can secure your network using a service mesh. Specifically, I'm going to go through a demo of how you can actually secure the communications between your applications running inside of Kubernetes, talking to a Redis database running on a VM, so that you can completely trust your network even in an untrusted environment. And I'm Nicole Hubbard, one of the developer advocates for Hashicorp. So when I'm talking with customers, one of the things I get asked the most is, what is a service mesh? And if that's not the question I'm asked, the question I'm asked is, why should I use a service mesh? And so these are two very good questions that hopefully by the end of this you'll understand the answers to. But before we answer those, let's get into a history of services. So when we started off deploying applications, we started with this traditional data center approach, where we had a firewall that acted as our perimeter firewall, blocked all traffic coming into our infrastructure. It allowed traffic to come in and hit our load balancer, and from there our load balancer sent out the request to our 3 application servers. And then we would sometimes have an additional zone firewall behind our web servers that would limit the traffic into our database so that we ensured only the web servers were talking to the database on the database port. And with this works well. Very clear boundaries. Nothing's getting in without coming through that exterior firewall. And the only traffic that is allowed is web traffic that goes through the load balancer. And so this approach works well when we're deploying monoliths. And when we have our monoliths, we've got different systems within the monoliths. So let's say we're building a ordering system. One of those systems could be our product catalog. The other one could be our payment processing. And all of those components within our application can continue to talk to one another as they need to. There's nothing that limits the communication between our order system that actually receives the order and the payment system that charges that order. We can just make in-function memory calls and we're able to communicate with the different pieces of our application without any problems. However, as we've started to grow and build more systems, a lot of people have started to migrate to microservices. And so with this, instead of a single service, we have 4 services now. They're still the same components. We've got our orders catalog, we've got our list of orders, we've got our payment processing. So nothing there has changed. But what happens is, how do these services communicate with one another? So how does our ordering system talk to our payment system? And so what happens is, a lot of times people will hard code an IP address between these or create a DNS entry that points to one of the servers. And so that starts to work well. But what happens when we scale out our service? And now all of a sudden our product catalog has 3 instances running. How do we actually know which one we're supposed to talk to? How do we keep that up to date? Do we just hope DNS updates quick enough that when we remove one, they're gone? And so one of the things a lot of people will do is they'll add a load balancer. And so this load balancer will allow us to have a single point that we can talk to our product catalog in this instance. And this works well, but the downsides here are we added an additional network hop, and we now have more infrastructure we have to maintain because we're maintaining a load balancer. Now, if you're running on a cloud provider, maintaining a load balancer is pretty simple. You click some buttons in the UI, use some Terraform, CloudFormation, whatever, stand up a load balancer. But in that case, you have additional cost now for your infrastructure, as well as an additional network hop that actually has to leave your network to go talk to the managed provider's load balancer. And so if we go back to our traditional data center approach, where we were deploying monoliths onto web servers, we actually start to look at what modern data centers look like. So in this case, we no longer have just our traditional data center. We still have it in place. But as we've grown, we've now added a new environment that has a firewall connecting these. So these environments are connected. And we're running a Kubernetes cluster now. And so inside this Kubernetes cluster, we're running all sorts of microservices. They need to be able to talk to a key value store like Redis. They need to be able to talk to, say, our MySQL database or Postgres or whatever you're using. And now we've actually had to replicate those databases so that services in both data centers can use those. And so our firewall rules have become more complex, and it's difficult to control and limit over the network with our standard networking approaches to limit that traffic between our services and our databases, especially for the services in Kubernetes, where say maybe only 2 of those services out of the 8 actually need to be able to talk to our database. But because of the way Kubernetes assigns pods and IP addresses, it's very hard to be specific in your rules and say only these 2 services can talk to my database now. You have to open it up to the entire cluster. And so as we start to deal with dynamic infrastructure, we start to run into 3 challenges really. And those are service discovery, service segmentation, and service configuration. And so what do those mean? So let's start with service discovery. And another key component to service discovery is a service registry. So let's go back to our example of service A and service B, or order system, payment system, whatever we want to call them. Service B comes online, and now what it needs to do is register with the service registry. And so this can happen in a lot of different ways. In the case of Consul running inside of Kubernetes, this can happen automatically. In the case of just Kubernetes by itself, this happens automatically with your service. When you define a service in Kubernetes, your pods for that register as that service. And so there's a lot of ways to do this automatically without having to change any of your application code or integrate whatever registry you're using into your applications. You can get this for free if you do the correct deployment process so that you don't have to make changes. All right, so now we've got our service registry running. We've got service B set up to register. So now we've got 3 instances. They've registered themselves with these 3 IPs. And so now service A needs to be able to talk to service B. And so service A can ask the registry, hey, where can I find service B? And the service registry will be like, hey, B lives at 1.2.3.4. And the nice thing is the service registry can do additional things for you like health checks. Say one of those instances isn't reporting itself as healthy based on the health checks you defined. The service registry can make sure that it doesn't return that service to your application that's asking for those, or that instance to the application that's asking for it. And now service A is able to communicate with service B, directly connecting to one another over that IP address. So this entire process is pretty simple. You got service B coming up, instances registering, service A asking the registry for, hey, where can I find it? And then that connection happening. Now, how you do that discovery will depend on the service registry you choose, as well as your deployment environment. But I will show a way that you can do this without having to actually make any application code changes as well to your application, so that you can actually get that discovery without making code changes and without interfering with the way your application is written and tying it to a specific registry. Now, service segmentation. So what do we mean by this? If we look back to our original example, we've got our monolith here running our 4 subsystems. We've got our database running on a static IP, the zone firewall that logs out traffic there, and our DMZ firewall that's between the load balancer or the outside of the load balancer. So in this case, there's not a lot of segmentation that has to happen. Our subsystems A, B, C, and D can all communicate with one another because they're the same running process. There's nothing to limit what can happen there. But as we break these into microservices, not everything needs to communicate with one another, and so we can actually start to do some segmentation. So if we look here, we can see that A needs to communicate with B, and C and D both need to be able to communicate with one another. And A and C need to communicate, and B and D. But there's no use case for B and C to communicate and A and D to communicate. So we can actually go through and create rules that say allow these services to communicate and deny any other services trying to communicate. And we'll actually show what that looks like here in a little bit in our demo. And so this gets really useful as you start to scale and have more and more microservices. I've actually interacted with some customers who are running upwards of 3,000 microservices where they're using intentions inside of Consul to limit the communication between applications that they're running so that their services can only communicate with services that they need to communicate with. And this adds great security to limit and ensure that nothing is being communicated with if something's compromised. And so another component is service configuration. And so what is this and what does it mean? So one of the big pieces when you're using a service mesh for service configuration is a certificate authority. How are you handling all of this authentication and encryption? And so you want a certificate authority so that you can generate these certificates, assign them to services, and use them for each individual instance of your service. And so inside of Consul, when we actually generate these certificates, we have SPIFFE certificates generated. They're your standard X509 certificates that are used by standard websites for all of your standard internet traffic. And these certificates are automatically generated and rotated as your services start and stop. So you're able to get these automatic without having to make changes, without having to individually generate these. And so this provides you the ability to have a zero trust network where nothing on your network has to be trusted because all of your communication will be encrypted with these certificates, and you can use these certificates to validate the identity of the request and who the client is for the request so that you know that you're talking to who you think you're talking to, as well as validate the server. And so now let's talk about the service mesh specifically. And the service mesh is made up of two components, really. You've got a control plane and a data plane. And in this case, I'm going to be talking about Consul as the control plane. And in the data plane, you've got proxies that run. These can be anything that meet the requirements for a proxy. In the case of Consul, we default to Envoy. And so I'll be talking about Envoy today. And so what happens is all of your traffic that flows only goes through your data plane. Traffic between your applications never goes into your control plane. It's only through the data plane. If your control plane goes offline, your data plane is still online and still has all the instructions that it has received and is able to continue communicating, assuming no infrastructure changes happen. And so this allows you to actually be able to remove requirements for when your servers need to be upgraded, where if for some reason something happens and you lose your servers, all of your control plane or all of your data plane communication can still continue. And so the next piece is the service access graph component, and this is what I refer to as intentions. And so in Consul, we can actually control the intentions via the command line. So we can do Consul intention create, deny, web server to everything. So now our web server is no longer allowed to communicate with anything. And then we can create an intention that says our web server is allowed to communicate with our database server. And these intentions will apply no matter where our service is running. So right now our web server might be running, or our web service might be running on web server 1. But what happens if we deployed our web server on, say, database server 3? Would it be allowed to talk to our database now all of a sudden because they're on the same machine? And in this case, they wouldn't, because these intentions will follow that service no matter where it lives. This is also really useful when you actually start to scale and you go into multi-cloud situations where your services might be running in multiple clusters or multiple VMs because you're spread across multiple environments. So your one set of rules will apply for your entire infrastructure. And there's also a web UI that allows us to manage these intentions. So we can go through the web UI of Consul and actually create and remove these intentions as we need. So as I've mentioned a few times, application integration. So all of this stuff seems really cool, but what do I have to do to make it work with my application? So Sidecar Proxies are your answer here. And so what happens is all of these happens with Sidecar Proxies. So you don't actually have to change your application. So in the demo later, I'm going to show running Redis on a VM using an Envoy proxy, and then running a web service, which in our case will be Redis Commander. And I've made no code changes to either of these applications. These are the standard containers for Redis Commander, and the Redis database is the standard Ubuntu package that I got with apt install. And what happens is we run these proxies next to our applications, and instead of our application talking directly to the database, our application gets pointed to the proxy server. And so now we're able to communicate to the proxy, and the proxy gets configured from the control plane, and it's able to communicate with the other proxy to talk to our database to secure that traffic. And this requires no code changes to our application, and we get secured encrypted connections between our web service and our database by making no changes to anything and not configuring any of the security. In the case of Kubernetes, which I will show, we actually have a injection webhook that you can use. So if you define the annotation of console.hashicorp.com/connect-inject true on one of your pods, this will automatically add all of the containers and sidecar proxies that you need. And you can use some additional annotations to do some additional configuration, and I'll show those in the demo. So for these sidecar proxies, the way things work is, say our web server wants to talk to the database. What happens is the web server initiates the connection to the proxy server, and then the proxy server is going to talk to the local console client that's running on the node that it's on, and it's going to ask, where is the database? And the console client is going to return the IP address and port for the database. And then that proxy server is going to open a TLS connection to the proxy server for the database. And then the proxy server for the database is going to ask its localhost console client, hey, is the web server authorized to talk to me? And in this case, earlier we created an intention that said that the web server was authorized to talk to our database. So the console client returns yes, and the TLS connection is established. However, had it not been authorized, the TLS connection would have just been terminated at that point. So what are some extra benefits we can get with this? So my personal favorite benefit that you can get as you start to deploy Consul Connect to get service meshes running is our mesh gateways. So what are mesh gateways? These allow you to actually expand your service mesh across numerous environments. Most service meshes are built to run within a single cluster. Actually, most service meshes are built to run within a single Kubernetes cluster, I would say. And with mesh gateways, we can actually run Consul service meshes on only VMs and use a mesh gateway to facilitate communication between our VMs running and our Kubernetes cluster services. And you can actually take this even farther and use this to go across clouds or your on-prem data center and a cloud data center. And it solves some interesting problems for you. So in this case, we've got two different environments. We've got our API and our web servers running in one data center using the 10.8.1.1 IP range. And we've got our database server running in our database server running in another data center using the same 10.8.1.1 IP range. Usually when you have two networks that overlap in IPs, connecting those together with VLAN peering or VPNs or anything along those lines gets to be very difficult, and you have to end up creating IP translation rules so that you can communicate. But with mesh gateways, we're actually able to put these at the edge perimeters of our data centers, and all of the traffic between the data centers actually will flow through these mesh gateways. So the API server doesn't say, hey, I want to talk to 10.8.1.2. What it does is it says, hey, I want to talk to the database. It happens to be running over in this data center. Can you connect me through the mesh gateway? So the proxy for the API sends that request to the mesh gateway for its local data center with the information that is needed to send it to the next mesh gateway. And then that mesh gateway will do some NAT translation for us so that it's able to communicate to the database proxy server, and then the traffic is sent back. And all of this is using those TLS certificates that we're generating. So you can do this over the public internet. And so all of this happens, and my favorite is you no longer need to create firewall rules or expose your services to the internet or even just to your other clusters. The only thing that you have to expose now for an entire cluster to be able to communicate with another cluster is the mesh gateways. And so this allows us to limit our endpoint exposures to a single rule that says our mesh gateways are allowed to communicate with one another, and that's it. And then all of that traffic is encrypted with TLS. Well, next we have our demo. So let's jump over here. So what I've done already is I've deployed a Kubernetes cluster, and inside of here, I've actually deployed our Consul server. So I used the Helm chart that we provide, Consul Helm. It's in GitHub. It's got standard values. I've overridden some of our values. So the only changes I made was I changed the name of our data center for our Consul environment to Nicole Redis. And then I enabled the connect inject, which we can see right here with our injector webhook, because we have one of those running. And then we have our 3 Consul clients. So this one right here are 3 clients, and we're running 3 Consul servers. The reason there's 3 clients is we have 3 nodes in this cluster. So this is running here within GKE for this case. And then what I've also done is I've deployed a Redis database server. And so this is running within GKE as well. And if we just take a look, you can see here that I've already installed Redis, and that Redis is running, but it's only listening on localhost for both v4 and v6. So nothing off of this server can communicate with it. And we can actually see that if we look at our IP addresses and we grab this IP here and Redis CLI, H ping. We'll see we're not even able to communicate from this host over its IP address on the network because it's not running and it's not listening for that. But over localhost, we are able to communicate. Oh, what did I do? Oh, typo. We're able to see that we're able to communicate with our Redis server right there. And so let's go ahead and set some stuff real quick. So let's set hello to RedisConf. And then let's set demo to please work. Oh, gotta quote that one. Even when I ask it to work, it's not gonna work. All right, so now we've got 2 keys set within our Redis database. And so what I've done is I've installed Consul following the standard instructions that we provide for installing Consul. And we can see inside of here, we have some config that I've set up. So the first thing is our standard Consul config. So in this case, I've set the data center to match Redis, Nicole Redis. I've set our data directory to just store all of the data for Consul in opt Consul. I've given a retry join. So these are the service IPs for each of the Consul masters running within our Kubernetes cluster. And then I've enabled local script checks. And so that is so I can do a health check on Redis. So then the next thing I did was enabled central config so that all of our configuration can be stored centrally within Consul for Consul. And then I enabled Consul Connect. So I just set that to true. All of this could have been in the one Consul config file. The next part was I defined our Redis service. And so this is pretty simple. I've created a service, I've named it Redis, and then I've created an instance of that service named Redis1. The port that this is running on is 6379, the standard port. And then I've enabled connect with a sidecar service so that we're using the sidecar that I talked about. And then we've got a check just to do a health check on our service. And it's called Redis check. And it runs this script that we've got right here. And so if we take a look, this is just a very simple script that does a Redis CLI ping and makes sure the result is Pong. As long as it is, we exit cleanly. If not, we throw that there's an error. Nothing complicated here. So inside of tmux, I have, attach, that's the command. All right, so we can see here, we've got a Redis sidecar running. So we're just going to run a Consul Connect proxy sidecar for Redis 1. And so this will create us a Consul Connect proxy. So this is the sidecar proxy I talked about. And it's a sidecar for the ID Redis 1. The name of this is proxy. The proxy ID for this specific proxy is Redis 1 sidecar proxy. Now, if you were doing this in production, you would want to make this a systemd service. You would not want to start this in tmux, but just to show this, I wanted to start it here manually and leave it running manually. And so we can see that when the proxy started, it loaded its config. We did not give any config. The only config we gave was the name of the service that it's running for. And so it talked to console and the control plane and pulled down all of that data. We also parsed a TLS identity. So we can see we've got our SPIFFE certificate that's generated by our CA that was automatically created for us with Consul using our Nicole Redis Datacenter and our services Redis. So we've already got a working TLS certificate so that we can identify ourselves. And now we can see that this has started listening, and it's listening on all of our IPs so that it is accessible outside of this node, and it's listening on 21,000. So anything within our service mesh can communicate with this over port 21,000. So we can go ahead and go out of there. And so what I've done here is I've created a port forward using Kubernetes so that we can forward the console UI to port 8080 on my local machine. So if we jump over here, we can actually see our services. And reload. We've got our console service, we've got our Redis service, and our Redis sidecar proxy. And when we look, we can actually see that specific Redis 1 sidecar proxy running on the node RedisConf DB. And the address is listening on 21,000. And the instance is going to use the node IP that's being registered. Then we can see that we're running an instance of Redis and that it's running on RedisConf DB and it's listening on 6379, which is what the proxy will use to communicate with it. And we can actually see our console servers are running as well, all 3 instances of those. And then we can see all of our nodes so that we can see we have our 3 GKE nodes, and then we've got our RedisConf database, and this is the IP that those services will use to communicate. And then we can actually look at our intentions. And right now we have an intention that says all services communicate with Redis. But let's go ahead and actually delete this. And let's create a new intention. Say we want our environment to be secure. So we're going to say that all services are denied from communicating with all services. So we'll set this to default deny for our description. And so now within our environment, nothing can communicate. And so let's come over here and let's look at our Redis Commander deployment. So this is a very simple deployment. All we're doing is deploying a pod. We're giving it a name, Redis Commander. We're setting a label on it. And then we're setting our 2 annotations. Our first one is connect inject. We're setting that to true. The next one is our connect service upstreams. And so what this is this is a list of services I want to be able to communicate with. And I've said I want to be able to communicate with the Redis service, and I want to be able to communicate that locally on port 6379. So then we deployed Redis Commander, and I'm just using the image that they provide, using the latest version of it, and this happens to listen on port 8081. So we can go kube control create, and we can give it this file. And we can see now that we've created our container. So now we can get our list of pods, and we can see we have our Redis commander running. But what's really interesting is right here, we actually have 3 containers running, even though we only defined a single container. So let's take a look at what happened real quick there. So if we describe this pod, we can see everything that's happened with it. But if we go up, we can see that we actually had an init container called Consul Connect inject init. And so this was added automatically for us. It talked to console and it registered our Redis commander sidecar proxies so that these were registered and configured to work. And we set our local bind port to 6379 as we defined. And we can see that it's using the proxy public listener, and it's using 20,000 to do its own health checks. And so this gets registered, and all of that happens in our init. And then we can come down and we have our actual containers that are running all the time with our service. And there's 3 of these, even though we only defined this Redis container. So we've got Redis commander running here with the latest image that we talked about, that we configured. And here's what it pulled down, listening on the port we defined. But then we have additional things running here. We've got a Redis Connect service port that was defined as an environment variable for us so that we know how to communicate with our service using environment variables if we need to. We've also got another container called the Consul Connect Envoy sidecar. So this is the sidecar I showed in those graphs. And so this pulls down a Envoy proxy Envoy Alpine image and runs it with us with the config already configured for us. And then the last container that we run is a lifecycle sidecar. So this one runs, does health checks, and ensures that our service is running, and that if anything changes that needs to trigger a restart of our sidecar proxies, that happens automatically for us. So now we can go ahead and let's go ahead and jump over here. Oh, let's actually keep control port forward Redis commander. And that was on 8081, and we'll just forward that to 8081 locally as well. And now we've got a connection to our Redis commander container on 8081. And so if we load up localhost 8081, we can see that we have a working instance of Redis commander. And by default, it's trying to access a Redis database on localhost. Currently, there's not one, because our intentions don't allow that communication between their services. So if we go back and look at our services now, we can see that in the process of starting Redis Commander, we now have a Redis Commander registered, and it does have a health check. And we can see that our sidecar proxy for Redis Commander is running, and that there's 3 instances, and they have health checks as well to ensure that those proxies continue working. And so if we go back over to our intentions, we can actually create a new intention, and we can say that Redis Commander is allowed to communicate with Redis and allow Redis access. So we'll go ahead and create that, and just about as quick as we can do it and switch back to the tab, we can see that this has actually already been able to connect. And so as this loads, we can actually just refresh everything just to make this force refresh. Well, whoa, where'd my data go? Yes, because I changed the intentions, our port forward has to be reset because it reset our service for us. And so I can see now we actually have our local host, and we've got our 2 keys that we set. So demo please work. Turns out it looks like it has. And we've got our hello RedisConf key. And so now all of this communication is happening through our secure proxy. This is all secured using those TLS certificates that were generated for us. And we did not have to make any changes to either of these applications. So when you're deploying applications that say you don't actually control the code of, this is great because you can actually integrate them into your existing service mesh without having to make changes and get all of the features that you want and that all of your other applications have. This also makes it possible to use any service mesh without changing your application codes so that you're able to secure this communication. Now, coming in our next release is a new feature that we're really excited about called terminating gateways. And what terminating gateways do is they work kind of like mesh gateways in that they secure your communication for you, but what they do is they secure the communication to a public endpoint. So say you're using a managed Redis provider. You're actually able to use the terminating gateway to communicate with that managed Redis provider, and all of the traffic for your applications will flow to that gateway, and then that gateway will communicate to the public endpoint or the private endpoint on your VPC that your hosted provider has provided you. And so you can still add all of those intentions to limit everything. So I'd like to thank you for taking your time to watch this, and hopefully this helps you with some ideas on ways you can secure your infrastructure using service meshes. If you have any questions, feel free to reach out to me on Twitter or my email, and thanks.